Yeah, and I'm really happy to be here. I'm fine if people want to ask questions in the middle, by the way. If there's a burning question at some point, I'm happy to answer it. Usually I tend to uh, talk quite fast on many different topics. Feel free to stop me by asking questions if you think it's the right time to ask a good question. So I titled this talk, Intelligent Architectures for Intelligent Machines. It's actually a bit broader than processing in memory and computing in memory. And you will see, I think, why that is the case. But I believe processing in memory still forms a central part of the design of future intelligent architectures that we want to design today. But there are also other dimensions, in my opinion, that we would like in such an architecture, as I will discuss. But I believe those dimensions are very critically important for enabling processing in memory or computing in memory as well. So hopefully this will be a more holistic talk that looks at the dimensions that are required, in my opinion, for intelligent architectures, part of which should be data-centric for sure, but also it should be data-driven and data-aware. And I think altogether, they will enable a much better computing in memory type of engine that minimize the data movement. Okay, with that, I will start with the major problem. I think nobody would disagree with this problem statement saying that computing today is bottlenecked by data. I will give you a lot of examples of evidence supporting this. And data is key for important applications: machine learning, AI, genomics, robotics. All important workloads are data intensive. They require rapid and increasingly more efficient processing of large amounts of data, because data is increasing at the same time. We want faster processing. Today, we can generate more data than we can process. And these are, just to give you an idea, some workloads that we are currently dealing with for sure. And these are workloads that are very data intensive, and memory is a bottleneck in them. Data leads to huge performance and energy issues. And these are some workloads that many of us are using at the moment, probably video playback and capture being an example, browsing, machine learning, inference, and training. Clearly, these are examples where data is a performance energy bottleneck also. But there are also workloads that are emerging that we have not been fully exploiting the benefits of. I'm not suggesting the previous workloads we're really fully exploiting, but there are even more emerging workloads like genomics and genome analysis. And we actually are able to right now generate a lot more data than we can process using the genome sequencing engines, because genome sequencing technology, the high throughput sequencing technologies have essentially been going through multiple revolutions in the last 2 decades, enabling us to sequence many, many, many more genomes in an exponentially increasing manner. And today, basically, we can sequence many genomes, but then we cannot analyze them fast enough. As a result, we have a huge computational bottleneck sitting between these machines that have a lot of capability to sequence genomes and the scientific discoveries that we're supposed to, or we would like to make, and medical advancements that we would like to make. So we would like to give these machines to doctors who can make very quick decisions within the course of seconds or minutes, not days or weeks. Today, some of the analyses that we require can take days or weeks. And data is a big performance energy bottleneck in these applications. We do a lot of work on this topic. I'm not going to talk a lot about genomics, but you can see that there are some devices. This is the Oxford Nanopore devices that can actually, at very low cost, sequence a lot of data. But then to analyze that data, we need very powerful computers, because we don't have mechanisms to do processing in place, in memory, or in device, if you will. As a result, data overwhelms these machines also. And if you're interested in this topic, I'm happy to talk separately, and maybe there's a panel discussion afterwards. But you can also read the survey article where we talk about accelerating different steps of genome analysis pipeline. And we also do work. This is a paper that was published in Micro, where we're looking at the approximate string matching problem and designing the algorithms and the architecture together so that we can much more efficiently and at high performance do this analysis without moving data a lot in the system. And future is going to be even more embedded, even more powerful in genome sequence analysis. These are the more embedded devices from Oxford Nanopore. You can see that these already exist. But again, we're bottlenecked by how fast we can process this data. We're moving data all around the system, at least to your computer. But for even more sophisticated analyses, we're actually moving data to data centers, essentially at the macro scale as well as the micro scale. We're doing a lot of data movement because we don't really provide the processing capability inside the device, inside memory, inside where data is produced, essentially. And if you're, again, interested in this, there are also lectures. Nima mentioned that we have lectures on my courses, as well as invited lectures that you can find online. So I'm not going to talk more about this application, but I believe there's a lot of potential in such applications. But essentially, my point is data overwhelms today's machines, including their storage and memory capability, communication capability, and in the end, computation capability as well, because so many of these computation units stay idle because data overwhelms them, essentially. And data also greatly impacts robustness, energy, and performance and cost, and we're going to talk about that a little bit. Whereas if you look at fundamentally a computing system, it consists of three key components: computation, communication, and storage and memory. And we have heavily optimized the computing unit, and maybe not so much thought about doing processing inside the memory and storage and communication units. And because of this processor-centric mindset, let's say, design paradigm, most of the system is really dedicated to storing and moving data as opposed to doing computation. If you look at a single node today, more than 90% of the hardware area is dedicated to caches, interconnect, other caches, other interconnect, main memory, other interconnect, storage, other interconnect, etc. Essentially, we call these devices computing devices, but most of the hardware resources are actually doing storage and movement of data. And this indicates that we don't have a balanced design in today's systems, clearly. Even though we want to do computation, we cannot because we're moving data to the processors. And to enable that movement of the data to the processors, we need to have a huge amount of infrastructure for storage and movement of data. So I'm going to elaborate on this a little bit more. And as a result, we see in applications data overwhelming modern machines. I'll give you one data point, which we will discuss later on a little bit more. This is a study that we did with Google a few years ago on these workloads that I showed you in this slide. And essentially, we analyzed mobile systems and found out that more than 60% of the total system energy while executing these workloads is spent on data movement in these devices. So my axiom going forward will be that if you want to design intelligent architectures, we want to handle data well. And I would argue that we want to design intelligent architectures because we're increasingly designing architectures that are going to be intelligent, and that will essentially make a lot of decisions for us, like self-driving cars or robots, etc., and who knows what else, and genome analysis systems. And we would like to not be overwhelmed in the design of these systems. We would like to be efficient, basically. So, of course, the question becomes how to handle data well. I would argue there are three major components to it. And the first one is really about data-centric systems. Basically, we want to ensure data does not overwhelm the components via intelligent algorithms and architectures. And more importantly, via whole system designs, algorithms to architectures and devices, essentially the entire stack, such that data does not overwhelm the components. This requires us to think more data-centric as opposed to processor-centric. So I think in conjunction with this, we would like to also take advantage of vast amounts of data and metadata flowing through the system to continuously improve the architectural and system level decisions that a system makes. Let me give you a very quick example. This is not going to be the major focus of this talk, since we don't have a lot of time. But for example, when we design a memory controller today, that memory controller has a hard-coded policy. And that policy doesn't really change. Essentially, that policy doesn't learn based on what it has seen in the past milliseconds, and certainly the 6 years that I own my computers, for example. Whereas there's a lot of opportunity to learn and adapt your policy to the data that's flowing, to the workloads that are executing, to the access patterns, etc., such that we can actually have a learning system, continuously learning system. So this requires us to rethink our components in a data-driven manner, such that we can design a machine learning-based system that can learn from its decisions. Okay, I'm not going to talk more about this, maybe except for the next slide. On top of this, I think we need to enable both of these, as well as to enable other opportunities, we need to understand and exploit properties of different data. We cannot treat all data the same. Whereas today's systems are treating most data the same, they don't know enough about the data and different properties. For example, privacy properties, security properties, approximability properties, different execution locality properties. If you want to actually really improve our systems and make them intelligent, we need to really understand what data we're dealing with and different characteristics of the data. So these are, I think, three directions for designing intelligent machines. And based on these directions, I think today's architectures are not good at dealing with data because they're essentially processor-centric as opposed to data-centric. We're going to talk a lot about this today with some examples. And we're also not taking advantage of vast amount of data and metadata that's flowing through the system. We're making systems designed with simple decisions, hard-coded policies. We're ignoring a lot of data. Essentially, the system is not self-optimizing or self-learning. Their systems we design are making human-driven decisions today, especially when we want to make machine learning a key component of our lives. Maybe the machine itself should learn to optimize itself going into the future as well. And on top of this, as I said, today's architectures do not know much about different properties of different application data. They mostly treat all data as the same, or they're oblivious to the characteristics of the data. As a result, they make component-aware decisions as opposed to data-aware decisions. For example, they do not necessarily know which data is more suitable for being executed in the CPU or accelerator or memory, for example. Maybe we can give that information a much better way. And certainly security and privacy criticality is also important. But there are many, many different aspects of data characteristics that I'm not going to talk about in this talk. So in this talk, I'm going to focus especially on the first part, data-centric architectures. But as I said, I think data-driven and data-aware are essentially things that complement the data-centric architecture, because all of these are really important, in my opinion, to make data a first-class citizen in designing our systems. Okay, so let's jump into the main part of the talk. So what is a data-centric architecture? When I sat and thought about what should be the properties of a data-centric architecture, I came up with these four. Essentially, the first one is what we're going to talk most about. We need to process data where it resides, as opposed to moving data all over the place. But on top of this, we also want to enable low latency and low energy data access, because data is, again, the most important thing that we're dealing with. So we should access it quickly and with low energy. We should enable data at low cost storage and processing. And there are a lot of ideas related to this, which I'm not going to talk about. And we should enable intelligent data management. Intelligent controllers should handle robustness, security, and cost, etc. So I'm going to touch upon this when I motivate processing in memory from a technology scaling perspective. Okay, now let's jump into processing data where it makes sense. This is the more general form, not just in memory, not just in storage, not just in the interconnect, but essentially everywhere. We would like to be able to have the option and ability to process data everywhere such that we can minimize data movement. That's what I would say we should really shoot for. And this is not a new idea, clearly. This is one of the earliest papers that were written on the topic by Harold Stone, as early as 1970, as you can see. And clearly, people have looked at this idea in many different ways. Harold Stone's argument at that time was cost, actually. Actually, it's a beautiful paper to read at this time as well. And I'm not going to go through all the literature of processing in memory that has happened over the course of 50 plus years. But what is different today is something I'm going to focus on. So why should we really take it seriously and try to enable it today? Basically, I think today we are kind of being pushed in two directions, and we have nowhere to escape but to do in-memory computation in many, many forms. We are being pushed from memory technology very heavily. Memory scaling, especially DRAM scaling, is becoming extremely difficult. I'm going to talk about that quite a bit in the beginning of the talk. We are putting controllers close to DRAM, and industry is very importantly open to new memory architectures. We're seeing actually movement from industry, especially in recent years, including recent months. So there are things like this happening, memory and controllers getting closer together through silicon via and more integrated architectures going into the future. And there are experimental devices that are changing the internal DRAM microarchitecture a little bit as well. And these are driven by memory scaling issues. And this is a paper that we wrote, invited paper that we wrote at the International Memory Workshop some years ago, 8 years ago, where we argued that memory scaling is becoming much worse. So we should really be thinking about architectures, memory architectures, in a very different way. And at that time, we didn't have a lot of evidence, but in this talk, I will give you some evidence to this. So this is a work that we did with Facebook that shows that memory scaling issues are making memory less reliable. This is we basically examined all of the memory errors that Facebook experiences over the course of 1.5 years in all of their data centers. And they have a lot of memory, they have a lot of servers. So this is a correlational study. And the key correlation is that is between the chip density that's employed in the server and the relative server failure rate that the server experiences. And you can see that there's a strong correlation across many, 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 many memory and devices. So basically, as memory gets denser, cells get closer to each other, and they become smaller. They become more vulnerable to noise, and overall system failure rate increases. If you're interested, I'm happy to talk about this further, but I'm not going to go into more detail. We also built a lot of infrastructures to understand such issues with FPGAs, so we can test real memory devices. And these are some infrastructures. If people are interested, actually, we have released these infrastructures. People actually wrote papers, including some on computing in memory that I'm going to mention in a little bit with this infrastructure. Essentially, this is an infrastructure that enables you to control memory devices using an open source memory controller. And you can do actually, you can do experiments like reducing the latencies to the DRAM devices and seeing what happens essentially. So while we were doing a lot of interesting experiments, we found out one thing that is, I think, a critical DRAM scaling issue, which is the fact that you can predictably induce errors in most memory chips, in DRAM memory chips. This is called the Rove-Hammer problem. Essentially, more than 80% of the DRAM chips that we tested were vulnerable at the time. Not much has changed, by the way. I'm going to give you more recent results in 2020 as well. But this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you find some other example, please let me know. And as a result, people are writing articles like this: forget software, hackers are exploiting physics. So essentially, memory scaling issues like this are threatening our security, fundamental security guarantees. So what is the problem? Essentially, this is a read disturbance issue in main memory that gets exposed to the user. That's the problem, basically, the fact that it gets exposed to the user, programmer, or any user, essentially. So basically, if you want to read a row from memory, you need to activate the row in DRAM. This is called activate in DRAM, apply high voltage. If you want to read some other row, you need to apply low voltage to this. Basically, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, activate, precharge, activate, precharge, activate, precharge in DRAM, which essentially enables you to read from this row, it turns out in adjacent, physically adjacent rows, you get bit flips. So this is not supposed to happen. Clearly, you're reading from this row. You should not be affecting anything else, including this row. But you're affecting some cells that are physically adjacent and actually flipping them from 1 to 0 or 0 to 1, depending on the vulnerability plus the encoding of the data. As a result, you're corrupting data. And this data may be belonging to the operating system, some other application, your own application. All bets are off if you actually are able to do this in a predictable way. And we found out that you could do this in a predictable way in more than 80% of the memory chips that were manufactured by 3 major manufacturers at the time. And this is a scaling problem because it doesn't exist in older chips. You can see that it first started.
Onur,
yes.
Maybe one question just to give also a break to people to process so much information. Can you go to the previous slide when you mentioned that you can do, by doing a hammering off, you can change the bits in the neighboring cells in a predictable manner?
Yes.
Does this mean that you can force the neighbors to predefine 0 or 1 ahead of time, so you know exactly to which bits you are forcing?
No, not the bits. Basically, okay, you know exactly which bits will flip. They're very predictable. So if you can flip bit 21 once, you can flip it again, basically, and again and again. So basically, you can profile and figure out which bits are flippable, and then land the page that you want to corrupt with some intelligent security engineering mechanisms to that location, and then hammer things, and then essentially flip the bits that you really want to flip. And people have developed attacks based on this basic templating, let's say, of attacks. Yeah, you cannot control that. You cannot necessarily control the data that gets over there, but you can control which pages are allocated to that location reasonably deterministically in some systems. I'm going to actually mention one paper.
Yeah. All right.
Okay, thank you, Saeed. That's an important point from a security perspective, of course. Okay, so you can see that this is a scaling problem. Essentially, older chips were not vulnerable because cells were not as close to each other and not as smaller. But newer chips are all vulnerable. Well, this is 2012 and 2013, but we will see later that chips from 2020 are even more vulnerable. I'm not going to spend a lot of time clearly because we're still motivating why we want intelligence in the memory controller. But as I mentioned, this is a security problem. I'm not going to go through this in a lot of detail. But when we wrote the paper first, we said that one can hijack your computer if you can predictably induce bit flips. And later, Google Project Zero essentially showed that. And they basically showed that by doing beautiful security engineering, you can gain write access to your page tables as a user level program. And you can essentially circumvent all of the security mechanisms in Linux. If you're interested, you can read their work. And later, there have been a lot of attacks. These are folks from TU Graz who showed that you can actually get unrestricted access to systems of website visitors by doing these bit flips in JavaScript. And this was the paper that I mentioned where you could do this deterministically in Android systems by carefully ensuring that the operating system allocates a security critical page table entry to a location that you know or that you figured out somehow was vulnerable. And more recent works show that neural networks that would otherwise provide you very good accuracy actually lose significant accuracy if you can do these bit flips in an intelligent manner, let's say. And this is work from Deliang. Maybe he can talk about it later on, where these folks showed that otherwise a very reasonably accurate network becomes essentially a dumb network, according to their picture, as you can see. That is not very good. So if you're relying on these neural networks on our life-critical, safety-critical applications, and if their accuracy can be depleted like this using bit flip attacks, then we have a big problem. Okay, so basically memory scaling issues are real. There's a lot more to talk about RoveHammer. I'm not going to do that except for a few more slides. But if you're interested in the solution really requires, I believe, more intelligent controllers, more secure controllers that can fix the problem. I'm not going to talk about the solutions in more detail. I will give you that the problem is becoming worse. Basically, this is data that we published in ISCA 2020, where we actually analyzed more than 1,500 recent chips, and we found out that newer DRAM chips are much more vulnerable to RoveHammer. You can induce RoveHammer after only 4,800 hammers. Existing mitigation mechanisms are not effective. We also showed that DRAM chips that are marketed to be RoveHammer free by the three major manufacturers are actually not RoveHammer free. What the DRAM manufacturers did was they incorporated some proprietary RoveHammer protection mechanisms internally inside the DRAM chips. They didn't say exactly how they work, but they said they're RoveHammer free and period. And everybody believed them. But this paper showed that you can actually bypass those mechanisms via intelligent reverse engineering. And there are other works that I'm not going to talk about. But there are, of course, solutions also, which we don't have time to talk about. But solutions, the key takeaway with the solutions is that you need intelligence in your memory controller close to memory so that memory controllers can detect issues like this and prevent them from becoming problems. Again, if you're interested, we talk a lot about RoveHammer and all of these papers in detail in our courses and other lectures. Okay, so I think this push is clear. We have a huge push from circuits and devices. They're not scaling. DRAM is not scaling very well. So we need more intelligence on the memory side to cover up for the lack of scalability. And I think one intelligence would be in-field patchability, which again requires intelligence to avoid these failures. But this is not the entire problem. There are also other scaling issues, which I'm not going to go over, which I'm in detail. Refresh, retention is a huge problem in DRAM. And that requires an intelligent controller to solve, in my opinion, because today we're refreshing everything at a fixed high rate. But if we're a little bit more intelligent, we can refresh things at different rates. But of course, this requires a lot of understanding and a lot of intelligence about the device itself, as well as how to do it, as well as error correcting codes and working together with system level reliability mechanisms, which we don't have time to talk about. So essentially, we need to push a lot of intelligence inside the memory to fix scaling issues like RoveHammer and retention time. And industry is writing papers about it too. I like this work that was published in 2014 by Samsung and Intel, which where they argue that to solve the DRAM scaling challenges, we want intelligent controllers as well. Another example of this is we're increasingly having hybrid memory systems, and hybrid memory systems enable different types of memory on at the main memory level. These different types of memory have different upsides, greens, and different downsides, reds. If you combine them, you would like to maximize the greens as much as possible and minimize the exercise on the reds as much as possible. But this requires, again, intelligence, in my opinion. This requires hardware and the software to manage the data allocation and movement to achieve the greens as much as possible. And that requires intelligent controllers as well. So there are many arguments, in my opinion, to have more intelligence on the memory side because of all these scaling issues. And this is a scaling issue also. We want hybrid memory systems because one memory technology is not scaling good enough, let's say. Okay. So that was the push from technology argument. We have a huge push from technology requiring us to do something intelligent on the memory side. But there's also a similar pull from systems and applications, I would argue, maybe an even bigger pull. And I will mention this in this slide. Clearly, data access is a major bottleneck. I'm going to give you even more evidence. Energy consumption is a key limiter. I don't think anyone would argue with that. But on top of this, data movement energy dominates compute energy in today's systems. So let's take a look at this. But before that, let me motivate in a different way. Basically, in my opinion, do we want the key question is this: do we want a future that's sustainable and efficient, or do we want a future that looks terrible for everyone in the world? I would argue that we want sustainability and energy efficiency, but we also want high performance to solve the difficult problems that we're trying to solve. But the problem is our current design principles in computing cause great energy waste, and at the same time, great performance loss as well, because we're moving data a lot in the system. And this is because processing of data is performed far away from the data. Again, at the macro scale, as well as the micro scale, within a computer, within a node, and across nodes, we're moving data a lot. As I said, this is because we have a very processor-centric view of today's systems. All data is processed in the processor. And when I say processor, I include the accelerators also, GPUs, CPUs, machine learning accelerators. They're all compute-centric machines, let's say. Yet we know that memory is the big problem. This is Dick Seitz, a quote from his one-page paper after he and his team designed the Alpha 21164 microprocessor. Basically, he said that we designed this processor to finish 4 instructions per cycle. It's finishing 1 instruction every 4.7 cycles in this important data-intensive workload. And he basically concluded this paper saying that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. There are many, many similar results. This is data from my own PhD thesis, where we showed together with Intel that most of the time, a state-of-the-art processor is waiting for data, not computing. And more recently, Google showed these results where they showed that most of the time, the processor that's executing all of their data center workloads is waiting for memory. The red parts are all waiting for memory, basically. It's computing only in this green fraction. And they have a lot more analysis, and I'd recommend you take a look at that paper. But basically, we have a grossly imbalanced system today. Processing is done in only one place. As a result, data moves a lot. This is energy inefficient, low performance, and complex. To overcome this, we add a lot of complicated mechanisms to the processor and the system and the software. We had complex hierarchies, mechanisms, multi-threading, etc. Many, many mechanisms, basically, in computer architecture are designed to tolerate memory access. And this, whenever they're useful, they're good. Whenever they're somewhat useful or not useful, like in random memory accesses, they become extremely energy inefficient, low performance, and add burden to the system, basically. And as a result, we have this picture where more than 90% of the system is dedicated to storing and moving data. Let me give you one more on the energy perspective. This is slides that I borrow from Bill Daly. You can argue with all of these numbers over here since they're old, as you can see. But the key takeaway remains the same. An arithmetic operation is cheap today in terms of energy. 64-bit double precision floating point, 20 picojoules. A DRAM read or write, 800x more energy consuming. So 800x may be too much, you could argue, but it's somewhere between 2 to 3 orders of magnitude today, basically. Memory access is much more costly in terms of energy. And there are other works that have shown this. Given this, does it really make sense to move data to the processor so that you can do a cheap computation on it? If you do that, this is the result you get. Basically, more than 60% of the total system energy is spent on data movement on important workloads that we care about. I would argue that we do not want to move data. We want to design systems that minimize data movement. So to be able to do that, we need a paradigm shift to enable computation with minimal data movement in the entire system, not just memory, not just processor, not just storage, but everywhere we should be able to do that. Compute where it makes sense, where data resides, and make computing architectures more data-centric. So of course, this is a big undertaking. Clearly, memory is an important place. And memory is very nice because there are some workloads that already are designed to fit memory because of its latency characteristics, right? We have in-memory databases, in-memory graph processing, and media processing engines. So memory is, of course, a good place to look at. And the rest of the talk will focus on the memory aspects, if you will. So basically, we would like to be able to talk intelligently to memory, ask the memory questions. Can you execute this for me? Memory answers yes, and here are the results. If the memory says no, go to somewhere else, then we will do that, basically. Basically, it's an intelligent system where all components are intelligent. Clearly, there are many questions over here. How do you design the memory and the controllers? How does the processor chip change after that? In-memory units change. How do you design the software and hardware interfaces, system software compilers and languages, and algorithms and theoretical foundations of computation as well? I'm not going to answer all of these clearly, but this is a problem that spans across the stack. That's what makes it really interesting and exciting. That's what makes the adoption also hard, because you will need to think about these issues, even with simplest changes to the memory devices. But the good thing is we can start with simple changes that can be potentially more easily adopted. So now let me go into 2 different directions reasonably quickly on how we can look at processing in memory. I'm going to mainly focus on DRAM, but the general ideas are applicable to any memory technology, in my opinion. You can minimally change any memory chip to do computation by exploiting the analog operational properties of the memory devices, as well as the existing organization of memory. And also you can exploit other technologies like 3D stack memory to do more near memory processing, if you will, as opposed to inside the memory processing where you're using memory to do the processing. Okay, I've already mentioned this. Basically, you can exploit internal connectivity to move data inside the memory or exploit analog computation capability. And who knows what else? I'm going to give you some examples. I'm going to start simple with data copy initialization, which is important. It's not computation clearly, but it's required to do computation. Basically, there are many cases where we do data copy initialization in our systems. Imagine initializing a 1 terabyte database. Imagine writing zeros to your physical memory to initialize that 1 terabyte. That's what happens today, basically. And that doesn't sound good, clearly. Can we do that better? That doesn't sound good because we go through the processor to be able to write those zeros today. And if you want to look at some data, Google in the paper that I mentioned earlier, they basically show that approximately 5% of all of the cycles in their Google's data center is spent only on these 2 function calls that do copying, memmove and memcopy. And there are other copying initialization that clearly happens. So how do we do data copy today? If you want to copy one page to another page, let's say small page, 4 kilobyte page, you go through the processor. You need to bring the data to the processor, do the copy, and write back the data. Clearly, this is high latency, high bandwidth utilization on perhaps the most important system resource in terms of bandwidth, causes cache pollution, and causes unwanted data moment, because if you're initializing a huge amount of memory, maybe you're not going to reuse any of that memory anytime soon. So for a 4 kilobyte page copy via the direct memory access engine, not even disturbing the caches, it takes about 1,000 nanoseconds and 3.6 microjoules. Of course, the question is, can we do better? And the idea is, why don't we just do it in memory? Enable all the mechanisms to do it inside memory and not disturb anything else other than memory, because we're just copying data. This is low latency, low bandwidth utilization, no cache pollution, and no unwanted data moment. I'm going to show you a mechanism that provides essentially more than an order of magnitude latency reduction and almost, between 1 to 2 orders of magnitude energy reduction. If you optimize it, I believe you can get even better. And the idea is very simple. This is just the core of the idea. Of course, you need to provide it inside the chip as well. But if the source and destination pages are in the same subarray inside memory, the idea is to do 2 consecutive activates such that when you do the first activate, the data of the source row gets copied into the row buffer. When you do the next activate, you implicitly deactivate the source row, and the row buffer drives the data that is latched into the destination row. So by doing 2 consecutive activates, you can clone one row to another row with negligible hardware cost. In fact, I'm going to mention a later work that shows that you can do this in existing memory chips by violating the timing constraints that you have very reliably. So if you want to do it really, really reliably, of course, you should incorporate this mechanism into your DRAM chip in a more reliable manner. So the latency and energy savings are significant, more than an order of magnitude, and between 1 to 2 orders of magnitude, as you can see in terms of energy. And clearly, you move data between banks across different subarrays. We have solutions to this that I'm not going to talk about in this talk, but you can read based on this paper and later ideas. Basically, clearly, there are extensions to this. You can enable data moment as smaller granularities within a bank, better interbank copies, and computation on data, which I'm going to talk about next. I'm just going to flash these slides, and these slides will be available if you're interested in these topics. I find these fascinating because I believe having a data movement and initialization substrate is key to enabling in-memory computation also, because you will need to rearrange data and move data internally. But the thinking is also important. The thinking is that memory is now an accelerator. Memory is doing things that is already very good at potentially, but we're not using it for. We're designing a lot of accelerators. All of them have a fundamental bottleneck, which is the memory bottleneck, whereas memory itself doesn't have that bottleneck. So why not put an accelerator that works really nicely based on the analog operational properties of the memory that you are dealing with? Okay, so similarly, in DRAM, we can support other operations like AND, OR, NOT, and majority. I'm going to go through this quickly by using analog computation capability of DRAM. And the key idea is by activating multiple rows, we can perform computation. And this leads to 30 to 60x performance energy improvement. I believe new memory technologies, which I believe Said will talk about in the next talk, enable even more opportunities because they're not limited as limited as DRAM, let's say, and they have interesting structures that can enable analog computation using current flows, let's say. And they can also operate on minimal data moment because they're non-volatile. DRAM is fundamentally volatile. You have to move the data at least a little bit whenever you are doing a read. So you're destroying the data. So you cannot get away without moving the data. But in some of these technologies, you can get away without moving the data. So what is the idea in DRAM? Basically, the key primitive is triple row activation. If you're able to activate 3 rows concurrently, in an ideal circuit, what you have is a majority function. So this is 1 bit in each row. Imagine you have 8 kilobyte rows, and imagine you're doing this on 1,000 subarrays concurrently. You're doing this bitwise operation on 8 million bits in a DRAM chip. And what you're getting is really based on charge sharing principles. If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So basically, this is a bitwise majority function, which is a beautiful function, and which can be expressed also as by setting C to 1, you get the OR of A and B, or by setting C to 0, you get the AND of A and B. So you can basically do bitwise AND, bitwise NOT, bitwise majority. Sorry, not bitwise NOT, bitwise AND, bitwise OR, bitwise majority. That's beautiful. And you can expose to the ISA, which I'm not going to talk about. It requires moving data to a special place where you can do the special activation with low cost, etc. I'm not dealing with a lot of these implementation issues. I will refer you to the papers that I will mention for those implementation issues. But in our opinion, this could be implemented at low cost, basically. So what's missing is, what is missing this from this being, what is missing is that we're missing a NOT. Basically, this and or not, and a NOT or majority is not functionally complete. But if you add a NOT, now you become functionally complete. And NOT requires a little bit more overhead. Actually, the complement of a value already exists on the other side of the bit line in the sense amplifiers, essentially. Basically, we want to feed that to a special row in DRAM. There may be other implementations that you may want to do, which I'm not going to talk about over here to minimize the overhead. But if you can do that, now you get a NOT as well. And if you can do that, now you get significant performance and energy reduction compared to DDR3. Sorry about this picture. I don't know why it didn't display well. But you can actually build NAND, NOR, and other primitives. I'm going to talk about the recent work where we can build any complex operation, actually. So this is good for some workloads that do bulk bitwise operations already, bitmap indices, databases, web search that is designed to maximize bitwise operations. And there are many other examples, some of which we have evaluated, some of which we have not. And if you actually map those applications to the substrate, to this in-DRAM computation substrate, you get significant benefits. This is, of course, all in simulation, right? Because we don't have the machines over here. And you can see that the query execution time reduces by 5 to 6.6x in this particular case. Some folks at the University of Wisconsin developed a bit weaving database. Okay, there you go. That we ported to our system because that bit weaving database was developed to maximize bitwise computation. And we see significant benefits when an application is designed to maximize bitwise computation. You can see that the performance improvements go up to 12x in terms of latency reduction for end-to-end queries. And you can see that the performance actually increases with the size of the data set that you have, of course, to a level. Once you fit in your DRAM chip and you have to go to another DRAM chip, then you need to minimize the communication across those DRAM chips. Okay, so I don't want to talk more about this, but you can read the papers on Ambit and the book chapters that we have written on this topic. More recently, very quickly, I will talk about some recent work that we've done in this area to make it more, essentially, to make it more generalized. And this is the framework that we proposed in ASPLOS 2021. And the idea is to have an end-to-end programming interface, ISA and hardware support for efficiently computing complex operations, for example, enabling matrix multiplications, etc. Provide the ability to implement arbitrary operations. So someone comes up with an operation, how do you actually map it to your DRAM substrate using the triple row of activations that we provide? And also, we want to have minimal changes to DRAM architecture. So without changing without making any changes to the Ambit architecture that I mentioned, we have this framework that can take a user input as a data flow graph potentially, and generates majority and NOT logic that's optimized using some principles that were developed at EPFL, for example, for some logic synthesis actually. And you can generate a sequence of DRAM commands, which leads to a SIMDRAM microprogram, which later gets triggered by these new instructions that can be executed in DRAM, and the DRAM essentially executes those new instructions. So if you're interested, you can take a look at this paper that introduced the framework. In my opinion, going forward, we need more such frameworks to enable in-memory computation, while also looking at the technology level to enable better mechanisms to do computation. So let me give you some work that others have proposed also. This is some work from Princeton that used our SoftMC infrastructure, where they actually showed that you could do row clone in existing memory chips without changing anything. Well, except for the memory controller. In the memory controller, you need to change the timing parameters such that you mimic consecutive activates. And in some limited fraction of the DRAM chips and DRAMs, they were able to demonstrate that you could do AND and OR functions as well. So I find this very promising because even though the DRAM chips are not really designed for cloning, row cloning, for example, or ambit-like AND and OR operations, you can do it by tweaking the parameters, violating the DRAM timing parameters. And imagine now what you can do if you actually go and design the DRAM chips to take advantage of this analog operational properties to do computation. Clearly, there is other work that looks at similar principles in non-volatile memories by doing triple row activation or more N row activation, if you will. They show that you can do it in emerging memory devices as well. So I will mention two other things. You can actually exploit the analog operational properties, latency reliability trade-offs, to generate physical unclonable functions in DRAM, as well as to generate random numbers inside DRAM as well. And I think we need to look at other things that we can do inside memory so that we can actually really truly enable a computing infrastructure inside memory. And security is really important, in my opinion. So we need these security primitives to be generated inside the memory by using the analog computational operational primitives. Okay, so that was the minimally changing memory chips approach. There's also another approach, which is, I think, more called near memory computing, let's say. I will briefly mention this as well, and then we will conclude. So basically, the other approach, which can be used in conjunction with the first approach, is 3D stacked memory. Essentially, we have 3D stacked memories that already exist, and other two three-dimensional technologies are under development. We have logic layers that have low latency, high bandwidth access to many memory layers today. So the key question is, can we take advantage of the logic layer to do computation? And clearly, there are many, many different types of 3D stacked memories that people were envisioning, and there's going to be more, in my opinion, into the future. And I'm going to cover two key questions very quickly. One is, how can we change the entire system to get the maximal benefits from this? Okay, let's step back after that. Can we not change the entire system and do simple function offloading to this logic layer? And what is the minimal thing that we can do in this system? Let's start with the maximal thing. Whenever you want to do maximal, I think it's good to think about customizing to applications. And when we first started doing this research, we wanted to look at graph analytics because graphs were important for everything. Today, graphs are really important for bioinformatics. In machine learning, for example, many machine learning frameworks are graph processing based. And scalable large-scale graph processing is challenging because it's really a fundamentally memory-bound problem. If you look at large data set graph processing, you have frequent enough random memory accesses. This doesn't mean that it doesn't have sequential memory access, but the random memory accesses dominate your execution time, and you have little amount of computation on those accesses. So to overcome this, we designed this accelerator called Tesseract, which is essentially an interconnected set of 3D stacked memory plus logic chips. You can see the interconnections over here. And each of this is a cube where you have many cores in the logic layer. Each core controls the memory on top of it. You don't move the data. You basically move the intermediate results as well as the functions between the cores. So we basically program these machines using remote function calls, distributed systems programming, if you will. And the data movement is minimized. You just invoke function calls on the data that's housed by different physical processors. Of course, graph partitioning becomes important. I'm not going to talk about all the details because it's a full system level paper, but you can imagine this as a GPU where you offload your graph computation to this distributed accelerator, and the distributed accelerator minimizes the data movement such that it can do the graph analytics really fast. Again, I'm not going to go into the details. You can read the paper. I'll give you some promising results. This was relatively old work. As you can see, later work actually improved our results, which I'm going to also mention briefly. But basically, at the time, this was the memory bandwidth we could get with hybrid memory cube. This is Tesseract, which looks different because memory and computation are combined. And we expose 8 terabytes per second memory bandwidth to 512 cores in this case. And the resulting performance improvement, end-to-end improvement on 5 graph processing algorithms is significant. It's about 14x using all the mechanisms we have. But later work actually did better graph partitioning, better load balancing, better interrupt processing, etc. And they actually improved this to about 2 orders of magnitude. And you can take a look at that. It's recently published at Micro 2019, for example. And the energy reductions are also commensurate. We can get basically close to an order of magnitude energy reduction. But again, later work improved this to almost 2 orders of magnitude, if you will. Okay, so let's talk about the simple function offloading, because maybe changing the entire system is too much. Because in that case, we changed the entire programming model. We got rid of virtual memory. Everything was physically addressed. It's like a primitive GPU, basically. But maybe over time, it becomes better. But maybe we don't want to wait that long. We want to look at these simple function offloading approaches. And this is the work that we did with Google. We wanted to understand where energy is spent on these consumer devices on important workloads that almost everybody uses. And as I mentioned, we quantified the energy cost of data movement, and we found out that it's quite high. And we wanted to look at processing in memory as a solution by offloading functions. But of course, the challenge in a mobile device is you have limited area and energy budget. So we wanted to be very minimal in terms of what we can offload. And the idea is to understand the workloads. And by understanding the workloads, we found out that data movement often comes from simple functions. And we designed lightweight logic to implement these simple functions in memory, either in small low power embedded cores or specialized accelerators. I believe you need a combination of both. You actually need some reconfigurable logic, in my opinion, to really take advantage of processing in memory. And overall, we found out that we can improve energy and performance by about 2.2 to 2.3x. It's not like the 15x that we discussed, because now we're actually becoming very limited in terms of what we offload, but it's still significant because you're not doing as much change to the entire system. Okay, I'm not going to go through these examples, but you can see some functions in TensorFlow are very data intensive: packing, unpacking, and quantization. And we basically identify those functions and offload them to the memory side. Packing is one example. Quantization is another example. And you can look at the paper for more detail. Clearly, there are many, many other functions from different applications like compression, decompression, and video playback and capture you can see also. Okay, so there are other examples of this, which I'm not going to go through, but maybe flash some slides. You can do this in GPUs, near data processing. You can do this in memory controllers to accelerate pointer chasing, which is latency critical, and many other things. You can accelerate prefetching. We're more recently looking at whole applications and using FPGAs with HBM, high bandwidth memory, as a way of improving performance and energy efficiency. And this is one example of that. That's even more far away from memory, near memory processing, if you will. And as I mentioned, bioinformatics applications are also a great fit for this. And we've also been looking at time series analysis, which is also very, very data intensive, and you want real-time performance in it. Let me quickly cover the minimal part, because I think minimal part is going to bridge us to the adoption issues. And one issue with processing in memory or any big paradigm shift is really adoption, right? How can we do minimal changes to adopt these? And the idea in this work is really to do that. And the idea is very simple, basically. We want to expose each PIM operation as a cache coherent, virtually addressed host processor instruction that operates only on a single cache block. This gets rid of a lot of issues with processing in memory. Basically, the idea is this. It looks like this. This keeps the sequential execution and programming model we're used to. No changes to virtual memory, minimal changes to cache coherence, and there's no need for data mapping because you're restricting the processing in memory operations to a single memory module. And the second key idea is dynamically execute where to execute this PIM-enabled instruction based on simple characteristics and predictors, which I'm not going to talk about. But let me give you an example of these workload instructions. So this is the programming model, basically. You have simple instructions turned into potential processing in memory instructions, and you have fences to ensure that all of the processing in memory instructions are complete before you move to later instructions. So a programming model is very similar to existing single thread programming model. But you can see some of the instructions that we came up with based on the workloads. In my opinion, having a customizable ISA is going to be very important going into the future, and potentially a reconfigurable logic layer inside the memory to be able to implement these instructions. But dot product is one example. Clearly, machine learning applications use that. Euclidean distance, clearly time cluster or time series analysis, stream clustering applications use that. But you can see many, many examples over here also. Ideally, we would like to have an infrastructure where we can generate these instructions and add them to the ISA and generate a substrate that can execute them as well. So what is the performance improvement that you get if you do all of this on some important applications that are listed over here, as you can see? Let me give you the large input set data set results. It's basically about 47%. So it's not 14x, it's not 2x, it's about 47%. So because we're minimally changing the system in this case. I would argue that this is not bad to begin with also, because we can improve on top of this. We can only improve on top of this, let's say. And the energy reduction benefits are also reasonable with simple changes. It's about 25% on a single node. Okay, if you're interested, you can read this paper for more detail. Now I'm coming to the end of the talk, basically, which is perhaps the most difficult part of the talk, meaning the difficult part of the adoption issues. We really need to think about enabling adoption of processing in memory. There will be various kinds of processing in memory, and I believe all of them are very important to examine, understand, case study. But we also need to think about how to enable the adoption. We need to look at the functionality of applications and software for PIM, look at ease of programming issues, interfaces, compile and hardware support. SIMDRAM was one example of this. We need to look at system support, how to enable coherence and virtual memory. We need to look at runtime and compilation systems to do things automatically as much as possible. Look at security issues, access control, and quality of service issues. And we also need to have infrastructures to assess benefits and feasibility in a reasonable manner. I believe all can be done, but we just need to change our mindset so that we think from a data-centric perspective. In the end, we will need to revisit the entire stack for sure, but I believe we can also get there step by step with as simple as possible modifications. I believe we need to look at all kinds of modifications, but we should not really overlook simple modifications that can get us one step at a time as well. Okay, let me give you some. We're also looking at different methodologies to offload things in an automatic manner to the processing and memory side. So this is a paper that's coming up at Sigmetrics, where we introduce a new methodology for understanding what should be executed close to memory. And we also will release a benchmark suite to evaluate data movement bottlenecks as well. I'd be happy to talk about this separately. But we cover a lot of other issues in this primary paper that overviews some modern issues in processing and memory. People may be interested in reading this. And this is an older version that looks at the workload and programming ease issues. Now, let me discuss some real systems. This is the UpMem system. They're based in Grenoble, and they already have a running system where they have simple cores associated with each DRAM bank inside a DRAM chip. And I think this is good news. This is a commercial system, and we're experimenting with the system. We also have another Sigmetrics paper coming up, which we will release soon, that analyzes the system. And we see a lot of really interesting, good results showing benefits compared to CPUs and GPUs in this system. And you can see that this is a general purpose system. Clearly, there are some programming idiosyncrasies, but it's a general purpose system where you can offload any computation inside the cores next to the banks. And clearly, you may have seen this announcement by Samsung, FIMDRAM announcement that happened in February in ISSCC, where Samsung, a big company, showed that they're also interested in processing in memory, finally, I must say. And they're looking at simple changes to the high bandwidth memory architecture to do simple operations that would accelerate what they call AI computing capabilities, essentially matrix multiplication operations, multiply and accumulate, and multiply and add operations. If you're interested, you can actually read the paper that they have. And clearly, they have some implementation that they presented in ISSCC. So this is good news, in my opinion, because the industry is finally taking this more seriously. And I believe there's more to come. And hopefully, the paradigm will change little by little. So if you're interested, there are more lectures on PIM that I'm not going to talk about. I've also delivered a tutorial at IEDM recently that is much longer than this talk. You can take a look at it. Let me quickly cover some of the key challenges. There are many, many challenges to solve. We've been etching into some of these issues, and other people in the community have been etching into some of these issues also, but there's a lot more to do in this area, like how to schedule code, how to maintain coherence, how to support synchronization, how to support virtual memory, how to design data structures, and infrastructures are also quite important. And we released some infrastructures for simulation. We're going to release one more with the Damu article in Sigmetrics. Okay, so this is the big challenge and opportunity for future, in my opinion. We want computing architectures with minimal data movement. And that will lead us to fundamentally energy efficient, in other words, data-centric computing architectures, and also at the same time, fundamentally high performance, in other words, data-centric computing architectures. Now, as I said, I think this is just part of the picture of an intelligent machine. We also want these machines to be self-learning or data-driven, and also understanding the properties of the data that they're dealing with, data-aware, so that we can really take advantage of all of these at the same time. But I don't have time to talk about this data-driven and data-aware aspects, but the slides are available. I'm just going to skip them in this part of the talk, but you can actually take a look at the slides on your own, if you will. I believe these three directions are actually quite synergistic with each other. So with that, I think I will conclude so that we can discuss more. So I believe going into the future, we need to design more intelligent architectures. They have to be data-centric, data-driven, and data-aware, which I think points to the fact that we need to design principled system architectures to solve the big problem we have with data. In my opinion, we're not handling data well, and it's manifesting itself as a memory and storage and interconnect problem. So if we design complete systems to be truly balanced, high performance, energy efficient, that will lead us to intelligent architectures. And I think these three directions will enable us to get there. So I think a key part of it is really enabling computation capability inside and close to memory, as well as wherever data resides or while data moves. I believe this can lead to orders of magnitude improvements. I've given you some examples of this. Enable new applications and computing platforms. I'm very excited about genomics platforms, for example. Enable a better understanding of nature as well, because fundamentally, nature is not really processor-centric, in my opinion. I don't know, I cannot claim to know how nature operates, but based on all the literature that we know about how brain operates, for example, we cannot say that it's centralizing processing in one place. And who knows what else, right? Okay, so maybe we can get closer to this machine and maybe supersede it, right? But I think to get there, we really need to think deeply across the entire stack while keeping in mind the adoption challenges, how to get there step by step. And I think we need to exploit good principles. These are some principles that I covered in the talk, actually, but I'm not going to go through them again over here. More importantly than anything else, perhaps we need more open minds, which means that we should really think different paradigms and be open to them and enable them. Because if we keep thinking processor-centric, we're going to shoot down a lot of ideas in different paradigms, for sure. And again, a lot of the talk that I mentioned here, a lot of the things that I mentioned here are summarized in this paper or expand on in this paper. And there are more references over here as well. Okay, with that, I will acknowledge people who have funded the research that I talked about. Please keep funding us. And certainly, I will acknowledge my students, postdocs, and collaborators whose work I have presented essentially over here. And if you want to know more about the group, you can read our recent newsletter that was published in January 2021. Okay, and everything that I talked about is really available online, and I will put the slides as well, but I think Nima will put the slides online as well on the webinar sites. Okay, thank you very much. Now I'm happy to discuss further with any questions or comments. Thank you.
Thank you very much, Onur. I will stop the recording now.